And now it's my great pleasure to introduce the plenary speaker, Ewine van Dishoeck. She's a professor of molecular astrophysics at Leiden University in the Netherlands. She's been working in this field of molecular astrophysics, I believe, for at least 45 years, which is quite some experience. It's, I think, no understatement to say that Ewine is one of the most eminent astronomers in Europe and certainly the whole world. So it's a great pleasure to have her here today. She's been involved in all kinds of frontline projects, including the European Infrared Space Observatory, ISO, the Herschel Space Observatory, the Atacama Large Millimeter Array, the world's largest ground-based astronomy project still, soon to be replaced by the 39-meter ESO ELT telescope. I worked with Ewine just last year in her current role at the IAU, where she works on global coordination, trying to get the nations of the world to work together in astrophysics. So please join me in giving a very warm welcome to Ewine. Thank you, Ewine.
Yes. Okay, good. Thanks very much, Jonas, for that very kind introduction. And thanks, everybody, for being here. Good morning, everybody. I hope you're enjoying the open readings. I just certainly have been enjoying listening to the talks this morning. So today, I've actually going to give a very general overview of the kind of work that we do in studying how new stars like our sun and how planets like Earth or Jupiter, how they are built, and then especially what the chemical composition is that is associated with that. So this is a talk for non-experts, so not for astronomers, but more aimed at the general audience that is present here. And one thing that I really like about the topic of astronomy is, of course, that the sky is everywhere. It's available to all of us everywhere around the world. And we have this fantastic phenomena that we see on the sky, such as this comet not so long ago that you could see with the naked eye. I don't know whether some of you have seen it also with the naked eye. That is already an indication that, not only do you start to wonder when you look up at the sky as to, what our place is in this universe and where we come from, but when we're looking actually at comets, we're looking actually at the building blocks of new planets. And they are full of molecules. That's many of the same ones that we also see in the clouds out of which stars and planets form. And just here also in Lithuania, and more general, I think here in the Baltic states, you actually have very good dark skies. So I found a few of these beautiful images here near the Molotai Observatory, not so far from here, where you see the Milky Way, but also in other places you can enjoy the night sky. Now, one of my hobbies is actually astronomy and art. And of course, as a Dutch person, I don't have to go very far because Vincent van Gogh just had to paint the night sky as he wrote to his brother Theo. And here you see one example of the Big Dipper here over the sun in Paris. But you see it throughout cultures, over the entire world. Anywhere you go, you will find something that has inspired artists in order to paint astronomical objects. And this is one of my favorites, and the Aboriginals, the indigenous people from Australia, that have their dreamings, in this case the Milky Way dreaming, that are sort of an integral part of their society, of how they live with these dreamings. And in this case, you see the seven sisters that are hidden by their mother in the center of the Milky Way, because Orion is actually chasing them. But 2 days ago, we were, or yesterday actually, we were in Kaunas, and here also in Lithuania. You have beautiful artists that are there. It's a wonderful exhibition. There are about 150 years of Kiordionis. All kinds of paintings actually associated with cosmos. And this is actually creation of the world. He had already 150 years ago, he already had paintings about how to make stars and how to make planets. This was at a time that astronomers, were just only starting to realize that stars didn't have eternal life, but that they were actually being formed and also enter lives again. And the same is also with planets. Okay, good. So take a train to Kaunas and go and see that exhibition. I think it's very worthwhile. So the night sky, the Milky Way, we can see in many of these beautiful images, especially on the southern sky. It's beautiful that you see the Milky Way. And what I like about this particular image is that you see not just the stars, but that you also see these dark clouds that are actually on the Milky Way, and that is actually where our origins is in the dark regions between the stars. And just if we would be able to go out of the Milky Way and look down on it, then what we would see is actually here in the center. We now know that there is a supermassive black hole. That was the Nobel Prize of 2020. But for the rest, our galaxy, the Milky Way, consists of some 250 billion stars, and our star, the Sun, is just one of those 250 billion stars. And we, of course, live on a rather small planet around that star, somewhere in the outskirts of the galaxy. So this already puts the whole question as to, how unique are we in a different perspective. Certainly the discovery of exoplanets by now some 25 years ago was one of the major sort of changes that we had in astrophysics in the last decades. So either we see the planet go in front of the mother star, then it dims the light a little bit, that's the transit method, or we see it because of the velocities that the planet induces on the mother star, and that we can also measure. But that has put many of these age-old questions, and they are really century-old questions. How unique is our solar system, and could these planets be habitable? It puts it in an entirely different perspective. And by now we know that there is an entire exoplanet zoo, actually. There, on average, every star has at least one planet, but most of them are of a type that we don't have in our own solar systems. Yes, there are Jupiter-like planets, or Saturn-like planets, or maybe Earth-like planets, but the bulk of them are of a mass and radius that are somewhere in between Earth and Neptune, so between 1 and 10 times the mass of the Earth. We call them also super Neptunes or mini Neptunes or sub Neptunes is what they are called. And sort of we've now moved sort of from the detection of these and finding these exoplanets to their characterization. What is their composition, and could some of them actually be habitable? And especially this category of planets that apparently are very abundant, but we know very little about because we have no analog in our own solar system. Yet our own solar system also tells us something, because we have the remnants of the planet formation process still here in the form of asteroids and in the form of comets. So asteroids have actually recently been visited by several missions, Japanese mission to Ryugu, and US mission OSIRIS-REx to Bennu. They've actually not only gone there, but they have actually brought back some material to Earth, and it's now being studied in exquisite details with very powerful instruments that we have on Earth. And they're telling us a lot about the inner part of the solar system, what happened there. The comets are not just rock, but they're also ice, half rock, half ice. And they're actually the Rosetta mission, by now about a decade ago, actually landed on a comet for the first time and also traveled with that comet for 2 years and sniffed all the gases that came out of that comet. And so we know a lot of the chemical composition of that one comet that was visited there by the Rosetta mission. And again, that is something that we can directly link with what we see in the earlier stages of planet formation. So both of these are messengers from the early solar system, our early solar system. And we can try now to put all of that in context, actually. So I know that some of you may be biologists, or even I know that there is also talks about the medical sciences here. So you may be working sort of in this part here of the sequence. What I'm going to talk about is really just the very first step here in the whole sequence of the emergence of life, as it may have happened on Earth, namely how to make a habitable world. And the main message is going to be that the building blocks for making that are actually quite common in the universe. So at least that first step may happen. It's up to the chemists and the biologists to figure out how to work the other steps that you see here in this sequence. Okay, so we're going to start our journey now, but first I want to pay tribute to my group, my fantastic group of students and postdocs and colleagues all around the world that have really put this whole field together, and it has been my privilege and joy of working with them, and I hope to give proper credit to all of them. Okay, good. Well, Orion, still well visible this time of year on the night sky. And one thing I'm trained actually as a chemist, to realize is that most people look at the stars, but very few people when they look up actually ask the question, what is in between the stars? And we now know since early 1900s that space is not empty, but that it is filled actually with a very, very, very dilute gas, much more dilute than any of the best ultra-high vacuums that you have here in a laboratory on Earth. And the denser concentrations of that gas we actually call clouds. And there's a very famous one here in the Orion Nebula, where you see over here in the sword of Orion. But we are not interested in these colorful parts, that is the hot ionized gas. We are actually interested in those dark parts, and because those are actually the dark and dense clouds, that is where we see star and planet formation. That's where we find our molecules. So why are these clouds so dark? Well, that's because they contain small solid particles. Think a little bit like sand on the beach, but then a factor of 1,000 smaller. So these are typically silicate material, also carbonaceous material. And what they do is they absorb and scatter the radiation. And that is why you cannot look deep into them. So here you see an example of the Carina Nebula, which has typical densities of about 10 to the 4 particles per cubic centimeter. Now here in this room we have about some 3 times 10 to the 19 particles per cubic centimeter. And even in a very good ultra-high vacuum, we still have some 100 million particles per cubic centimeter. So when an astronomer talks about a dense cloud, it is really still very, very empty. So keep that in mind. It's also very cold, just barely above absolute zero. And so that's why for a long time people thought that there would be not much chemistry actually going on in these clouds. The other reason that people thought not much chemistry was going on was because we know that hydrogen is by far the most abundant element in the universe, made already in the Big Bang, and that the other elements that we need to do some interesting chemistry, like carbon, nitrogen, and oxygen, that those are actually down at the level of a few times 10 to the minus 4 with respect to hydrogen. So it's not only cold and empty, but it's mostly hydrogen. So the chemically interesting elements meet each other only very rarely. And so that is why people thought that they would not be having a rich chemistry. So that was actually the surprise that since sort of the first molecules were detected in the 1930s, but then when millimeter telescopes opened up in the 1970s, that's when the whole zoo of interstellar molecules started to be detected. And here is, don't try to read all of this. This is just to give you an impression of the enormous variety of molecules that we have. A lot of carbon-bearing molecules, also inorganic molecules. These are just going up to 7 atoms, and here now is going up to 13 atoms, one of the longest. Carbon chain molecule that you have here, HC11N, that has been detected. So those of you that are chemists, you see already that there are both saturated organic molecules, but also unsaturated molecules. So for example, that HC11N has 11 carbon atoms and just 1 hydrogen atom and a nitrogen. And that in spite of the fact that hydrogen is 10,000 times more abundant than carbon. So that tells you already that the chemistry is not at all in what we would call thermodynamic equilibrium, but that it's really determined by the individual reactions, the two-body reactions that we have in space. We also see some aromatic molecules now. This is one of the latest discoveries just earlier this year, that molecules like cyanopyrene are actually detected in space. And it's a big mystery still of how we make them actually under these very tenuous and cold conditions. Also fullerenes have been seen, and also polycyclic aromatic hydrocarbons more generally are seen actually throughout the universe. Okay, so how do we actually know that these molecules are there? Well, we have 2 ways of looking at their spectroscopy. In fact, we can also look at their electronic spectrum, but we can only do that in very diffuse clouds. But the bulk of the molecules are detected either by their rotation, but they do the overall end-to-end tumbling that they do in space. And we can observe that, for example, with the Atacama Large Millimeter Array. Or you can have a molecule that can be stretching itself. That's the vibrational modes. And that is what we observe in the infrared. It can either be stretching or it can be bending. And now we have the latest here is the James Webb Space Telescope that we can actually observe with. The millimeter part has, or centimeter also has the advantage that we can observe both simple but also these very complex molecules. So by far the bulk of the molecules that I showed you by now, more than 350 different types of molecules, have been actually detected through the millimeter technique. And down also to very low abundances. So this is extremely precise spectroscopy that we can do. With a resolving power that is fully resolves the line profiles at a resolving power of 10 to the 7. So we can actually measure abundances down to 10 to minus 12 with respect to hydrogen. The infrared is not so sensitive, but it has a big advantage. It can see molecules without a dipole moment. And there are some very important molecules. Think of CO2, think of acetylene, C2H2, of CH4. These are all symmetric molecules that don't have a millimeter signal, that don't have a rotational spectrum. The other big advantage is that we can see not just in the gas phase, but that we can also see in the solid state, actually, the molecules. But we have lower resolving power and not so much sensitivity in terms of abundances, but extremely important information that we get from that. Now, astronomy is actually driven by new big facilities. Every time we open up a new wavelength region, and so we can see sharper than we have ever seen before. And I've been fortunate over my career to have been part of this discovery space, so to say, with the Herschel Space Observatory, the Spitzer, with ground-based telescopes that we've had with ALMA, with JWST, for which we have data since 2022, and especially for the younger generation, the extremely large telescope is already being built in Chile, a 39-meter diameter. So once you finish your PhD here, look out for positions that make use of the extremely large telescope. It's a wonderful opportunity for you to do that. Here you see it's building, and now already this is from a year ago. It's already closed the dome. Good. All right, good. So the interstellar clouds have a very rich chemistry. We observed that by looking at their line profiles. So here is an example of a spectrum, in this case from the Herschel Space Observatory. And this is just to show you, this is not noise, this is just to show you if you blow up even the tiniest little part here, then you see all of these lines and you can beautifully fit them very accurately with a combination of these molecules that you see over there. So this is, and usually of every molecule that we firmly detect, we can see at least 3, but usually hundreds of lines. And so we really know that the molecule is there. There's no doubt about it. So one of those molecules is actually ethanol, also that you saw on that list that was detected. And this is to show you that if I think you have maybe some drinks later in the conference, that you can always tap a beer also from an interstellar cloud. Although with respect to hydrogen, it's of the order of sort of 1%. There are some other interesting molecules for the chemists here. This is ethylene peroxide. It's actually a chiral molecule. So this was the first chiral molecule that was detected. We cannot yet distinguish left and right-handed, but at least we know that some of these molecules are there, and it will be interesting to see whether there would be any difference in left or right, also in space. I mentioned also already the fullerenes and the pHs that are present. On the other hand, amino acids have not yet been detected in space, in spite of the fact that they have been claimed many times in the popular press. But they have not yet been firmly detected in interstellar space, but perhaps it's with now the new facilities that we have, it's not so far away. So far I've talked mostly about the gas phase, but there's a real direct interaction between the gas and the ice. So these interstellar grains, they actually act as a deep freeze in which atoms from the gas can actually freeze out on them. And once they freeze out, then they can actually be react with hydrogen, something that is difficult to do in the gas phase. So that is how you can turn oxygen into water, carbon into CH4, nitrogen into ammonia. And then actually carbon monoxide, which is one of the very stable molecule, which is triple bond, that actually, when it freezes out, can be hydrogenated with 4 hydrogens, and then you get actually methanol. So we sometimes say that the alcohol is literally on the rocks, actually, in interstellar space. And we even have some bubbles in it as well through the CO2 that is present there as well. Now, this actually has led to a whole study of surface science, actually as applied to interstellar chemistry, because there are lots of processes that are actually not well studied in chemical physics, but that are very relevant for interstellar ices. And that's because the ices are much thicker than not just 1 or 2 monolayers that a lot of surface science techniques are studying, but we are looking at very thick ices that are bombarded by photons and all kinds of heat and all kinds of other processes. And that's also why we have in Leiden our laboratory for astrophysics, which was under my direction for a number of years, and then Harold Linnaerts, who unfortunately passed away last year, was in charge of it. And that is where we try to sort of simulate some of these processes. We can go down in temperature, that's not the problem. But of course, we have to speed them up because generally it takes in space some 10 to the 5 years for reactions to happen. And so we need to speed that up to about 1 day. But then we have methods for extrapolating that to interstellar space. So here is some of our setups that we have in the laboratory. And it's actually thanks to that combination of laboratory experiments and also simulations and also observations, especially with the Herschel Space Observatory, that we now think that we actually know how the bulk of the water is formed in space. So this is a little simulation, and once a day a hydrogen atom lands on the grain. It may find another hydrogen, make molecular hydrogen, but can also find an oxygen, or the two oxygens can find each other. They can make even hydrogen peroxides. All of these intermediates we've also seen in the experiments and also in space. And then we make a few hydrogens, and now we speed up. We go from a few days simulations, now we go to 10 to the 4 or 10 to the 5 years. And this is how we think that we make sort of these icy mantles on these interstellar grains. So this is actually the way in which most of the water is made in dense clouds out of which solar systems formed, including our solar system. And that led one of my colleagues to say, well, if you think about it like that, you know, the water on Earth may be actually older than the sun itself, because the cloud still first had to collapse to form the star, but the water was already there. So think about that the next time that you drink a little bit of water, that what you're drinking actually is water molecules that are some 4.5 billion years old, and that were made in the cloud out of which our solar system formed. Of course, they have sublimated and recondensed, but a lot of the initial bonding was already done here on these tiny interstellar grains. Good. So this is an example of a measurement. This is actually in a planet-forming disk, where with the Herschel we measured actually the signal of water. And from the position of the line, we know it's water. And from the strength of the lines, we can count how many molecules there are actually. And we used a unit here that is more easy to imagine, namely the unit of oceans. So the number of water molecules that we have in this particular planet forming this is about 6,000 oceans available. So that's plenty. I mean, we have 3 oceans and we are a habitable world. So 6,000 oceans in this particular disks looks like plenty of water available to make a habitable solar system. Whether it does it, that's still a question, of course, but it certainly has a lot of material. So when we are doing these observations, actually the Big Bang Theory also even became interested in some of the water, and as you can see here, indicated on their whiteboard. Good. So to summarize this part, we have seen that there are lots of molecules in space in spite of these cold and tenuous conditions. There's both a lot of water and there is complex organic molecules, and they are found throughout the entire Milky Way. And actually, in terms of composition, there's a large similarity also with comets. So the building blocks for prebiotic material are widespread. Okay, so let's now go to the other part, namely how do we make out of these clouds a planetary system? Well, such a cloud can remain stable for quite a long time, but eventually gravity takes over and it will collapse under its own weight, and it will follow a protostar at the center. But because the cloud has a little bit of angular momentum, that means that the material cannot continue to fall in radially, but part of it will end up in a young disk around the star. And it's actually in these rotating disks that you see here in this little animation that's of gas and dust, that the planets can form, and then they can actually also carve out an inner part there of those disks. And so this scenario for making planets is entirely consistent with what we have here in the solar system hypothesis, the solar nebula hypothesis, because all the planets are also in one plane and orbiting in the same direction. So thanks to ALMA, we can now actually observe these disks, and we can see that they are full of structure. So this also actually came as a surprise, but we think that rather than smooth this, the fact that they have structure is actually an indication that there may be planet formation in action going on in these disks. And if you just now look at a gallery of these disks, you see that they have all kinds of structures. There are rings, there are spiral arms, there are asymmetric peanut structures. So this is really all telling us that something is happening in these disks. It doesn't necessarily need to be planet formation, but we think that at least in a fraction of these cases where we see all these beautiful structures, that is actually where planet formation is ongoing at this moment. What we're doing here is looking actually at the dust emission. So this is actually millimeter-sized dust, and especially these rings here that we have are what we call dust traps. These dust traps here, that is where you can actually lock up quite a bit of the dust. So to summarize this part, we now know that nearly all the young stars are actually surrounded by these disks, that they have sizes and masses comparable with our own solar system, and that the masses of most of those disks are enough to at least form some planets, not necessarily always giant planets, but certainly the smaller planets. And that all the structures that we are seeing, they point actually to planet formation in action. So the ingredients for planet formation are also common wherever we look in our solar neighborhood. Okay, so this is also a conference that is of the, the Universities of Technology. So let me say a little bit about technology, because astronomy is, of course, driven by these new facilities. So here's our disk, and if I now would put it on this image of Carina, then, okay, it becomes very, very, very small. And that was actually the reason that ALMA needed to be built, because we needed to be able to zoom in on these kinds of clouds and image actually these disks. So ALMA is a collaboration, a worldwide collaboration actually between Europe, North America and East Asia to build this array of some 66 antennas in northern Chile. And it was inaugurated in 2013. And I always like, why do we go to Chile? Well, that's because it's truly high and dry that you see over there. But the transporters that you see over there have been upgraded a little bit to these sort of gigantic food trucks that you see there to drive one of these antennas up to the high side. And then all these telescopes have been put into an array, and together they actually follow an object on the sky. And then the signals of all of these antennas are correlated with each other in a giant computer. And in that way, you can synthesize an image that is much sharper than what you would have with a single telescope. Good. Well, the other very important new mission is, of course, JWST, and this was a very emotional moment there when the last stage of the Saturn V, sorry, not the Saturn V, the Ariane 5 rocket was actually releasing it, and especially the solar panel that is then open. That was the last that we actually saw of Webb before it went on its journey to where it is at the moment. So Webb has actually 2 spectrometers on board that are very useful for observing molecules. And here you see the MIRI instrument that we were involved in, and also the other instrument, the NIRSPEC instrument. So it's really thanks to thousands of engineers, technicians, managers, and scientists that it took 30 years to build this for it to come together. So let's actually follow a little bit, what do you do in these 30 years? Well, first of all, you need to argue that these instruments have to be on the telescope. So that was the role of the scientists in the late 1990s to say what kind of instruments they had to be on board of this mission. And we pushed a lot for having a mid-infrared instrument on board, and because that was not that clear at all in the beginning, but then it actually happened, and we were very, very good that we got that, managed to get that on board. Then we had to build it, of course. Here are some of the components that we made actually in the Netherlands. Then it was integrated in UK. The UK had the lead of the instrument on the European side. Then it was delivered to NASA in a big Boeing in 2012. Then it was integrated in Goddard in 2015 together with the other instruments. And then it was, of course, also integrated with the telescope. So here you see the telescope being put together and tested. The golden eye that you see already is all of the segments. And then the instruments are basically on the back of the telescope. And then from Goddard, it went to Houston to do a full end-to-end test. These are actually the original although slightly modified, but still the Apollo chambers where the Apollo missions were being tested. Big enough and also cold enough in order to do this testing. So that was really an end-to-end testing. Then I went actually to Los Angeles. That's where the sun shield, a very critical element, had to be put on that. Then it went from Los Angeles to French Guiana on a boat. And that's where the launch is of ESA. And then, because the largest, why did why did ESA launch that? Because the Ariane 5 is the rocket which had the largest nose. You need to have space to launch, to put in your telescope, and the Ariane 5 had a 4-meter diameter nose. Now 4 meter is not large enough because JWST is 6.5 meters, so that's why it had to be folded, and that's why you see it there that it's actually folded, and then it's put there on the top of that. And then it was launched, as we've seen, and then it traveled from the Earth past the Moon to its current position at L2. That's a very stable point where they balance each other, the forces and of the Sun and the Earth. And then it travels actually with the Earth around the Sun. And the sun shield is always such that it is blocking the radiation from the Sun and the Earth and the Moon, because it's looking at heat radiation, and of course those are the main heat sources that you have. So what makes Webb unique? Well, it's big, 6.5 meters. Here you see a 1-to-1 scale model, and because it's big, it's of course more sensitive, and it can see sharper than any of the other missions before. Also, it has different eyes than some of the other missions like Hubble. So Hubble worked really in what's visible, where it is what our own eyes see. You know, of course, about the radio. We talked about ALMA in the microwave. There's X-rays, but Webb works in the infrared, and that is why you have to go to space, because a large fraction of the atmosphere is blocked by the water and the CO2 in our own atmosphere. So there are 4 instruments on board of Webb. And I mentioned already the spectrometers, the MIRI spectrometer and the NIRSpec spectrometer. These are not just simple instruments, they are actually what we call integral field units, in which you get a spectral image. So you get not just one spectrum on the sky, but you get a whole, sometimes more than 100 spectra all in a spectral image actually on the sky. And that is the power actually that we have now with these instruments. So they are much more sensitive. There's a huge discovery space that we're only just starting to explore actually with Webb. So you've undoubtedly seen beautiful images that Webb has been returning. This is a composite actually of the NIRCam and the MIRI, and everything that is red is actually where action is happening, where star formation is happening. So this is just one beautiful example. Here is another one, the cartwheel galaxy, interacting galaxies, which triggers star formation, and that's why you see all of this activity occurring. These are the famous pillars of creation, but now seen by the MIRI instrument. It's a little bit of a spooky image. It came out on Halloween. Actually, you see now with MIRI very clearly the young stars that are forming, because they stand out as the point sources, the red point sources in these images. That's really clusters. You see also there a whole cluster of young stars now being formed, something that we couldn't see with previous instruments. And of course, this beautiful image, which is of a cloud that is actually being illuminated by bright stars. You see actually some of the gas evaporating, but you also see some of the young stars actually in the clouds, and also their jets actually trying to push away the surroundings. And again, lots of point sources that are young stars that are actually in the cloud. Here's actually an analog of what our own sun could have looked like when it was only 10,000 years old. So this is a very young protostar. We can't see the star itself, and that's a PowerPoint star that is there in the center to guide your eye. We can't see, even for JWST, we cannot see where the protostar itself, the sensitivity. But what we can see is this outflow, this gigantic outflow that is coming out of it. And we can even see that it is periodic. We see all of these bullets actually in the jet. That tells us that the star has been accreting maybe every 5 or 10 years. It has been eating something, and then it has been spewing it out again. So this star is now on less than tenth of a solar mass, and it may still be growing up to about half a solar mass. It's still really being formed. So this is from one of our own programs, and that nicely went into the cover of Nature, although they turned it around and made it different colors and all kinds of other things to do with it. Going more to the spectroscopy, this is an example of the Copenian cloud by one of my Leiden colleagues, Melissa McClure. What you see here is again a NIRCam image, but the interest is here in two stars that are actually behind the cloud. So these are background stars that we can actually look through with Webb and look then actually what is along the line of sight in these clouds. So we observe the light of the star minus whatever is in the absorption. So here's an example of such a spectrum. So we see the dashed line is the background star. That's the continuum of the background stars. And then you see all of these very deep absorptions that are eaten out of this spectrum. Those are ices. Those are ices, and we can identify them thanks to our laboratory experiments. We see the water stretch, 12 CO2, 12 CO. We even see the 13 CO2. We see CH4, methanol. We see simple molecules, but also already a hint of more complex molecules. Incredibly sensitive. We are now looking at 10 microjenskis, about 1,000 times better than anything we were able to do before Webb. This is another source from our JOICE program that's where we are now actually zooming in to just a tiny little part between 7 and 8 microns. That's a region which is a fingerprint for more complex organic molecules. And with Webb, for the first time, we had actually the sensitivity to see those complex molecules. So we've identified not only CH4, but also some of the more larger molecules, organic molecules that we have, including ethanol, actually, but also acetic acids and formic acid that we have there. Also, interestingly, salts. Salts are quite present in stellar space, NH4+, but together with the negative ions, OCN- and HCOO-. So NASA thought that this was interesting enough to pick up as a press release. So they called it Cheers because of the alcohol that was discovered there. And then they realized that the combination of some of these molecules that were detected made a very nice margarita in space. And so that is how it got sort of propagated on the websites, both CNN and Space and CBS, etc. So that was a lot of fun to see how that is actually being picked up by the popular press. Okay, just in the last few minutes of my talk, I want to talk more about these disks and the planetary systems that can be formed. And this is actually an engraving that we have at our home. It dates from 1798. But this artist already, way centuries before exoplanets were discovered, already thought about, other planetary systems could be there, and they don't need to look at all like our own planetary system. So in the center is our own solar system, as it was known at that time, 7 planets, subcomets. But the other planetary systems either have more planets or fewer planets, closer by, further away. Lots of diversity, actually, of planetary system. And so the origin of that diversity must really lie in these planet-forming disks, in these rotating disks of gas and dust. And that's where a lot of research is actually being done, both to explain these beautiful ALMA data, but also here to just try to understand how do you grow something from that is a micrometer in size to something that is, first a kilometer in size, and then ultimately something that is 10,000 kilometers in size. You need to cover some 13 orders of magnitude in growth there. So you see here how they stick and how they collide. And because we know that the ices are full of molecules, this is also how the molecules basically get into these building blocks of the clouds. So this is mostly in cartoon form then, how we think that a planetary system is built. You start from these tiny little dust grains and they grow to planetesimals. That's the size actually of the comets. Those are the real building blocks. That's where gravity underneath is taking over. And then you make the planetary embryos. And then you can make a planet that looks like our own Earth or looks like something completely different. And that diversity is now something that we're really starting to explore also with JWST. Because ALMA has been beautiful in probing the outer part of planetary systems, of planet-forming disks. But JWST is really sensitive to the gas in the innermost part. And also seeing some of the ices. And so an important concept is here that of snow lines. So you all know about snow lines here in nature. This is Mount Fuji. The snow line is a location where the molecule is 50% in the gas and 50% in the ice. And that has long been recognized to be an important distinction also in our own solar system. Because in our own solar system, we also have a snow line. Well, in fact, we have more snow lines. We have the water snow line, but we also have the carbon monoxide snow line. Inside it, we have only the rocky planetesimals. Outside, we have the icy planetesimals. So inside, everything is gas. Outside, it is ice and rock. But now we have one of these icy grains, and they lose, due to friction, they lose angular momentum, and they can actually drift inward. And when they drift inward and cross the water snow line, they actually enhance the gas in water. But alternatively, they could actually also be sort of trapped in the outer regions of the disk in one of these dust traps that we see so beautifully with ALMA. So this grain may actually be stopped here. It may never cross this snow line, and thereby not adding water gas to the inner part. So whether or not you are actually making a habitable planet, whether you get enough of that water into the inner disk, and make a habitable world, that's because that's the inner part is where the terrestrial planets are being formed. That depends a lot on the structure and the dynamics of these disks. And that's something that we're now starting to realize with Webb. We have a guaranteed time program led by Thomas Henning that is called Minds, where we have a nice group of people together to look at about 50 of these planet-forming disks. And the main message is that we see enormous diversity. We see some of these disks that are very rich in water, and that would be entirely consistent with this idea of drifting pebbles that enhance the water. But this is another example here, and this is actually a disk with a large cavity and two known young planets, where we also find actually water in the inner part, terrestrial flowing part, where we have that water in spite of the strong dust traps. But there are other disks, and especially the disks around very low mass stars, so stars that are only 20 to 30% or less, 10% of the mass of the sun. They turn out to be incredibly rich in hydrocarbons. What we see is almost no water in this particular case, but we see very strong signs of acetylene. Orders of magnitude more than for the solar mass disks. And at the moment, we are trying to understand what is happening. And I was yesterday at a meeting in Kaunas, where we talked a lot about carbon and carbon grains. And, could these carbon grains actually be destroyed at 500 Kelvin? What is the nature of these carbon grains? So very interesting discussions yesterday here, actually, in Lithuania, that were very relevant for these kind of observations. So one thing is that, well, maybe we have indeed an enhanced carbon or a depletion of oxygen, but there's clearly changing chemistry along this disk, and it really depends on where your planet is being formed, on what kind of planet you have. And if you relate that to our own Earth, our own Earth, of course, has Jupiter. Jupiter acts as a big stop sign for any of these dust grains moving in. And we know that our Earth is carbon poor, it's also water poor. And that could be related to the early formation of Jupiter, actually, in our solar system. In fact, we are a very carbon-poor planet, and this actually links to some of the things that could have happened in our own early Earth. All right, I would like to end with this little video here, animation of one of our planet-forming disks. This one is only a tenth of a solar mass, but just to show you how rich it is in carbon-bearing molecules. We see CH4, we see here acetylene, ethane for the first time. We even see the 13C isotopologue of acetylene, HCN. Well, there it comes. All of these molecules are basically waving at us. Benzene for the first time that we detect very clearly, CO2, also the 13C isotopologue. And then here we have cyanoacetylene. And now we get to diacetylene, and now we actually are running out of the catalogs for the line identifications, actually. So just to show you that there's a very rich chemistry going on in these disks, and that there are literally thousands of lines that we can now detect in these disks. Okay, good. Well, I've hoped to have shown you how we are now using molecules to trace this whole trail from clouds to disks to planets. Is the chemistry really set already at that early stage and inherited all the way to planets? That is actually one of the scenarios, and there's quite a bit of evidence that a lot of the chemistry is already set in the early stages and then preserved when we form at least the planet building blocks. But there are also various stages where you can actually reset it, and that is what we also may be seeing in some of these cases. So next steps are, of course, making again the connection with the solar system, making the connections with exoplanets, beautiful data from JWST also on exoplanets. And then, as I mentioned already, the ELT that is coming, and that will be a wonderful opportunity for you to look at. Okay, good. Let me just end with one more message, and that is that just some iconic images here of the Apollo 8. And here, actually, of our own Earth, the pale blue dot that Carl Sagan suggested that we take with the Voyager mission, turning back once more and looking back at Earth. And we see just what a tiny little home we have. So as somebody who comes into this field from chemistry, I must say I find astronomy an incredibly exciting area to work in, lots of inspiration. But it also provides us with perspective, and that's, I think, is very important, especially in these days. A little bit of a sense of vulnerability. We are that tiny little dot there in space. Some modesty, and also tolerance. We better take well care of our planet, because it's the only planet that we have to go there. And so I'd like to end with the IAU 100 years motto that we had. And that is that we're all world citizens living under that same beautiful sky. Thank you very much.
Thank you very much, Ewine, for a very beautiful presentation and very interesting presentation. We have time for a few questions. Arnes.
Okay, thank you for the presentation, very nice. And like we heard in the previous talks in the morning, there are many planets, many stars with planets and so on, but most of the systems discovered are quite different from the solar system. Now, in the solar system, we have this very nice boundary of rocky planets and gas planets, which seems not to be the case in whatever other systems. Is there like a chemical rule or law, or from chemical perspective, why it should be rocky at the closer range and gas at the other range, or vice versa?
Yeah. So that's indeed the case that, of course, this whole idea of an ice line and that was important for making the cores of giant planets, that they were formed very close to the ice line. That dates back several decades, and then it was all thrown into the into confusion when the first hot Jupiters were discovered, when the Jupiters that are very close to their parent stars. But then people started to realize that, well, we actually cannot make a hot Jupiter so close to the parent star at 0.1 AU or something like that. They need to have formed somewhere further out and then likely brought in some stage. At least I haven't seen any realistic model yet that can build a giant planet really so close to the parent star. So I think people are now coming back, and all kinds of scenarios for planet formation, and they keep coming back to the fact that at the ice line, that's really where you have a concentration of mass, and you just simply build your cores of giant planets faster than you can do anywhere else. As to the question as to chemistry, it's mostly gas and ice. I mean, it's really temperature that is controlling so much. And especially water, which is the main ingredient. You just add so much to your mass by freezing out all of the oxygen and water that you basically enhance it.
Okay, in the back.
All right, really nice talks, really inspiring. As you pointed out, there are chiral molecules in space. And ideally, I would want to put a gas chromatography mass spectrometry system in a satellite, or send it out there. And I know it's probably difficult given the environment of space, but mid-IR spectroscopy should also be able to tell you if molecules are left or right-handed.
Usually you need polarimetry for that. So yes, indeed, gas chromatography you cannot do except for solar system objects where, that's, say, cometary studies, that might be possible. But basically the remote sensing, we cannot distinguish. I think you would need polarimetry in order to distinguish the light, the left and right-handed. So people have been saying, okay, well, if you're looking with polarized against a nebula that has polarized emission, maybe we could see something. But I'm not sure that we will ever be able to to have the sensitivity to detect that. Yeah.
Thank you.
But certainly, when you go to comets or asteroids, well, not so much comets, but asteroids, you can already see the difference between left and right-handed, where you can do in situ analysis. Yeah.
Okay, one more question.
Hello, thank you very much for your presentation. It was very interesting. I have a question regarding the argument that you kind of gave that so these protoplanetary disks, they are very common, they are abundant, that the organic molecules, they are abundant in the nebulas and in the disks, that water is abundant in the disks. So I guess like for me as an amateur, I would say there's a lot of indirect evidence that there should be life somewhere else. But I kind of want to hear your opinion, like as an expert, what other piece of evidence do you need to see to reach the conclusion that there must be life somewhere else?
Yeah, well, that's, I think, the big $1 million question, many billions of dollar questions for the next decades, is what is actually, proof that there would be life on other planets. We know the ingredients are there, we know that there are young planets there, but if you look at our own Earth, clearly just water is not enough. Not even just water and ozone is enough. You need to have some mix of oxidizing and reducing molecules, like CH4, maybe like nitrogen oxides present there. And even then, there's a lot of discussion among the experts there as to say, okay, what really constitutes evidence that there's life? People, of course, are looking at the vegetation edge in the visible part of the spectrum, but that's, of course, based on vegetation like we have on our Earth, and that doesn't necessarily need to be the vegetation that is on other planets where they are living. But that's exactly why telescopes like the ELT and the future missions like the Habitable World Observatory that's now on the drawing books of NASA, why they are being built is to try and answer that question. Some people think it happens already very quickly, and there was some noise in the popular press just a few weeks ago about dimethyl sulfide, which I don't think is evidence for life yet. But it's, in my view, it's going to take still another 50 years or so before we will have an answer to that.
Thank you very much, Evina. Let's give another round of applause.
Thank you. And I just want to say I brought a few postcards from JWST, especially for the non-astronomers. If you want to pick up some cards or want to give them to your friends, your non-astronomer friends, feel free to pick them up here and enjoy them. And all the best with the rest of your conference. Yeah.
But before we do that, we have three brief presentations. The first one is from Astrolight, and we'll be hearing from Anana Boretite. Please come.
So, hi everyone. I'm from Astrolight, and I'm the founder's associate. So I would like to give you a brief overview. What would it be like for you to work at a company such as that? We are a Lithuanian company. We work with lasers, so it's quite related to the things you're studying, at least for some of you. So before I start, I would really like to ask, just for my interest, how many of you have heard of Astrolight? Okay, some, but I guess we need to do more events like that because it's only some. So fun fact, Astrolight is actually the third biggest space company in Lithuania. Why is it a fun fact? Because we are only 20 people. So space industry in Lithuania is still rather small. We have a big leader here, Nanoavionics, who has many more people, many more employees, and they have quite big contracts right now. But Astrolight is also doing rather well, and we're expanding very quickly. So I'll give you a brief overview of what we do. So first of all, Astrolight started as a spin-off from this university itself. So we have our amazing founders. One of them is right here, Martynas. Our CEO, Laurynas, maybe you've heard of him. He actually was one of the initiators of the first Lithuanian satellite, Lituanica. He also was one of the co-founders of Nanoavionics, and he started Astrolight together with these wonderful people. So Astrolight itself currently is 5 years old, but we already achieved quite some impressive things. So just last year, we got recognized as ESA Rising Star. We also were one of the top 10 selected NATO Diana innovators, which is a really big deal because it was hundreds and hundreds of companies that applied. And currently we're collaborating with NATO Diana on various other projects. Also, talking more about the products, we are first to market optical ground stations as a service. So that's something that you will be hearing about, I hope rather soon. And we also, which is a very big thing for Lithuania in general, we will have an in-orbit demonstration end of this year, beginning of next year, of our Atlas terminal. So that will actually be the first Lithuanian laser in space. So we're saying Q1 because everything with space gets delayed. So even though it's scheduled for end of the year, it will probably be beginning of next year. So what is the goal? What is our mission? We, as Astrolight, would like to become a go-to company for space-to-Earth optical connectivity. So not only that, but we also want to become like a network provider, which would have various optical ground stations all across the Earth, and at the same time have a cluster of our laser terminals flying in LEO. So why laser communication in general? Why did we create Astrolight? So basically there is a problem. Satellites currently generate a lot of data. And it's very difficult to downlink this data because radio frequency currently is limited. We have slow data rates. It is rather congested right now. And at the same time, it's becoming more and more easy to jam. So this is when Astrolight comes to help radio frequency, because if you're studying physics, you might know that there is an issue with laser, which is rather simple. Bad weather, there's clouds, there's rain, the communication will not happen. The laser beam will not penetrate the clouds. So this is why we are coming as a helper to radio frequency to help them carry the burden and help them to downlink this data much faster in much better rates, and at the same time to reduce the cost, because radio frequency has expensive licensing, and with laser communication we're able to reduce these costs by 70%. So a little bit about our products. So currently we have 4 of them. So this is our cool guy. So this is the one that will be flying in LEO in space next year. So currently we're working on Atlas 2, which is our second iteration product. The one flying will be Atlas 1. So Atlas 1 is capable of 1 gigabit data downlink. Atlas 2 will be capable of more. And our next iterations, well, because laser communication has no limit, will be capable of even more. OGS, so our optical ground station. If you've seen RF stations or some other optical ground stations, you might notice that this one is rather small. So because we created this portable version that is easily deployable, basically, what is the thing that we're doing is the box right here in front, and there's also a receive head at the bottom of the telescope. So the receive head is able to receive the data from space, and this box in front, it looks like this. This is our uplink laser beacon system that is also possible to integrate with other optical ground stations, and it's possible with it to send data to space. We also have Polaris, which is our optical terminal for ship-to-ship communication. So if you've communicated with somebody who's Navy, you might hear that the way they communicate between ships is rather old school and rather weird. They still use these little lights, the flashing lights, to communicate a message. So this is also a problem we're trying to solve with laser communication. Again, difficult because at sea you can find mists. It's difficult weather conditions, but we're trying to tackle it. And we have a public public project with Lithuanian Navy, which we're gonna test out in the next few months. So 2 of our terminals will be tested. So hope if you will follow us on LinkedIn, please check on the progress here. And then one of the message, because I know that soon most of you will be looking for careers, right? For jobs, for next opportunities, maybe for PhDs. So maybe some of you would actually like to put your name on Lithuania's first laser mission to space. Because very soon, or even now, we're looking for some of these positions. So we're gonna be looking for optics engineers, laser engineers, software engineers, FPGA engineers, electronics, and some more administrative positions. And at the same time, we have a rather exciting opportunity in collaboration with European Space Agency. So we're actually gonna provide a PhD opportunity for industry PhD, meaning that the person will be able to select the topic. Of course, it will have to be connected in some way or another to laser communication, but it can be about basically anything. It can be about optical vortices, it can be about atmospheric propagation, or any other topic of your choosing. And at the same time, we'll provide industry knowledge and testing facilities such as labs and all the other equipment. So it's a rather rare opportunity because there's only several laser companies in the world that are doing optical communication. So we would gladly have somebody from Lithuania to have this opportunity, because we still seek to source most of our talent locally, because we want to support the industry and fantastic talents such as you guys here. So should you have any questions, or you would be interested in any of the opportunities, feel free to take a picture. These are our contacts. You can definitely send us a message or an email. So thank you so much, guys. Best of luck with the next steps of your careers or whatever else you decide to do.
Next, we have a presentation from UVRESO, Vincentas Adonaitis.
Testing, yeah, okay. Hello, everyone. It's a pleasure to be here and to present UVRESO in space and our propulsion technology, and to be more specific about our Hall effect thruster. And to start off, I will briefly discuss how it works and what is the Hall thruster. It's basically thruster, electric propulsion thruster that is being used in our spacecrafts, and a simple working principle of this thruster is that we have a propellant that commonly used is xenon, is injected into our thruster channel through the anode. Then it's being ionized, and the resulting ions are being accelerated by magnetic or electric field, and then producing our thrust. So these thrusters are mainly used for satellites, and the application is for their positioning and also orbital maintenance, and the most crucial one is for deep space missions. At UVRESO, we are currently expanding our expertise in this field, and especially to using the bismuth as a solid propellant for changing the xenon. And our goal is to create a thruster in range from 100 to, in power range from 100 to 500 watts, and it will also lead to more extended mission duration time, compared to xenon, and it would also help us to create have a safe space, which is crucial for today's space industry because every kilogram counts, and also xenon is very expensive gases, and it also has limited supplies, and because of that, the solid propellant would help us to reduce and be more cost effective. On the slides I provided here is the basic processes that our bismuth will have in the thruster, so just melting, evaporation, ionization, and that's producing the thrust. Currently, UVRSA has three main projects today, and currently the running simulations for magnetic and electric field topology studies, and that's basically tracking our electrons and ions, how they move in the thruster channel and exit plane. Also, we have the experimental work that will be our test bench and vacuum chamber for looking how our bismuth will be evaporating in the vacuum chamber. And looking ahead, we in the late 2025 will have a bigger vacuum chamber to really know the specifics and even to test our thruster, and that will be it. But we really trying to actively looking for PhD candidates for bismuth Hall thrusters for cathode development, and also if anyone is looking and is interested in this kind of specific topic for developing these thrusters and for simulation, modeling, or even experimental work, feel free and don't be shy to contact us. And yeah, thank you for attention.
Thank you very much. Our next presentation will be by Andrus Plečkaitis. He is the leader of the Business Innovation Center for the European Space Agency, and he'll be talking about how in Lithuania it might be possible to create and apply a variety of technologies for space applications.
May I use the mic? Okay. Hello, everyone. It's a pleasure to be here. My name is Andrus, and I would like to tell you a bit of what do we do and how companies like UVRSA, you just heard about what they're doing, incredible stuff, how they are supported actually in Lithuania. So I guess a few years ago, nobody really understood what is the space ecosystem about here. Now it's much more mature, and I would say we have a very good opportunity using our connection to ESA. Who knows what ESA stands for? Okay, great, quite a lot. So European Space Agency, which we are now an associate member of, we have a great opportunity to use their expertise and support new companies, because this is very new businesses. This is very like new area, new market, let's say. Because space is just another market. It just has very specific requirements in terms of whatever, environment, temperatures, vibration, vacuum, you name it. But we are not looking only at upstream, so-called upstream startups. We are looking also at startups who use the satellite data, which means that yeah, you don't necessarily need to fly. All right, so this is one of the biggest incubator networks, accelerator networks in Europe. 32 ESABICs altogether. So we have one in Estonia. We had we supported them in Latvia last year. And here in Lithuania, we started actually more than 2 years ago. So what do we offer? Actually, it's a lump sum. It's 50K euro per startup plus a top up of let's say average 10K from Vilnius city, which is actually for startups operating in Vilnius. We offer technical support in case you need some deep technical expertise. We expect that some of the startups we actually select, they have already deep technical knowledge, but they may lack space-related expertise. Then we offer business support because you obviously would need somehow to build a business model and approach your future customers. So what is the what are the opportunities for getting more exposure, for getting first validation of your products? These are all the topics we discuss with our startups. We also offer your access to international community, so not just ESA, which is all over Europe, but also some specific industry events like Space Tech Expo in Bremen and many events in Europe and also outside Europe. Yeah. And then there are already some experts because like the biggest business in Lithuania, nanoavionics, is 10 years old already. So yeah, I guess more than 10 years old. So you can already talk to people who were actually starting the company, but now they're business angels. And they are part of our community. So I would rather skip most of the rest. We have now 10 incubated startups and alumni. So the first alumni was SenseMetry, a model-based systems engineering company. They graduated last December. And we have like 9 startups already in the incubation, including JWST. And we just selected 3 more startups last week. So this year we have a goal, as every year, we have a goal to select up to 5. So not necessarily this year, but maybe sometime you will face an opportunity to join a team who will be applying. So yeah, you're more than welcome to check it out. And yeah, these are the partners we have, including Fizinių ir Technologijų Mokslų Centras. All right, so I think we can get in touch if you are interested to learn more. And yeah, please feel free to approach me. Thank you.